All right, so Elon Musk doubled down on turning Earth orbit into humanity's ultimate AI supercomputer, declaring that Starship will launch hundreds of gigawatts of solar-powered AI satellites every year within the next 5 years. Now, remember, this is all Elon time. Today, we'll unpack his latest post on X and that bombshell moment from the recent US-Saudi Investor Summit, where Elon and Jensen laid out the roadmap to terawatt-scale intelligence beyond Earth's atmosphere. I have Brian Wang and Chris Starsson with me today. Brian is an expert deep tech analyst, investor. He's a futurist thought leader, and he runs a prominent science blog, nextbigfuture.com. He also has a YouTube channel by the same name. And Chris is the CEO of Digital Habitats Corporation. I really need to get a longer introduction for you, Chris. Welcome, gentlemen. It's great to have you back.
It's great to be here.
Great to be here.
Let's first take a look at some of Elon's most mind-bending posts on X, where he lays out the future of AI data centers in space. So this is from the 9th of November. Elon says, with the advent of Starship, there is finally a path to solar-powered AI satellites at massive scale. It's the only path I can see that would allow for deployment of 1 terawatt per year of AI. This is from the 19th, where Elon says Starship should be able to deliver around 300 gigawatts per year of solar-powered AI satellites to orbit, maybe 500 gigawatt. The per year part is what makes this such a big deal. Average US electricity consumption is about 500 gigawatts. So at 300 gigawatts per year, AI in space would exceed the entire US economy just in intelligence processing every 2 years. Solar cell production for terrestrial applications is already far above this number at greater than 1,500 gigawatts of annual production capacity. Tonnage to orbit will be solved by Starship. And the Tesla Terafab is needed for this, as there is otherwise no solution at sufficient scale. And we'll come back to the question of terafabs and why Elon is so keen on building terafabs again through this conversation. And then this from him on the 22nd, where he says most people don't know that Tesla has an advanced AI chip and board engineering team for many years. That team has already designed and deployed several million AI chips in our cars and data centers. These chips are what enable Tesla to be the leader in real-world AI. And this is important. The current version in our cars is AI 4. We are close to tapping out AI 5 and are starting work on AI 6. Our goal, he says, is to bring a new AI chip design to volume production every 12 months. We expect to build chips at higher volumes, ultimately, than all other AI chips combined. Read that sentence again, as I'm not kidding. A lot to unpack here in these 3 posts of Elon from X. Before we get onto that soundbite of his, what are your immediate reactions to these 3? What do you see him laying out? We have 3 major problems. We've got the chips, the problem of the chips, insufficient energy. And if you want to build AI data centers in space, you need a vehicle that can get you Mars to orbit at scale at extremely cheap costs. Brian, let's begin with
you. When I've run the numbers as Elon has done in terms of order of magnitude, right? When he says 300 to 500 gigawatts, if you can run the numbers, you can see like how many megawatts of solar power you can get in one Starship load, right? The Star Cloud people estimate about 40 megawatts per Starship, right? But right now it's currently more like 6 megawatts. This is assuming you get to your version 3 satellites, where you have 68 kilowatts per and all that kind of stuff. The current Falcon 9 does just shy of 30 V2 minis, and they each have 28 kilowatts per. So 30 times 28, you're just shy of 900 kilowatts going up per Falcon 9 launch. And then you go to 6 megawatts in a roughly basic Starship, and then there's tweaks and improvements you can get to 40 megawatts, right? So let's, for simplicity's sake, use 40 megawatts. Then to launch a gigawatt, you need 25 times that. 25 launches to do a gigawatt. And then for 100 gigawatts per year, you're looking at 2,500, right? This can easily go up to 5,000 or something like that, again, without having quite the efficiency on that. So he was talking about that and saying you maybe go up to 5 times more than that, to 500 gigawatts under the ideal case. So that is going to 12,500 launches per year. One of the reasons you hit that limit is that even using natural gas and methane, which is abundant, natural gas is abundant, when you get to those kind of launch volume numbers, Starship starts using up significant fractions of the natural gas production of the United States. Because I'm putting my launch sites in the United States or off the coast or wherever, then you start hitting to like 5%, of all natural gas production in the United States, right? So you hit these physical limits, right? Also, there'd be like how many launches you ship through the atmosphere, that kind of stuff. So then he talked about 100 terawatts per year on the moon, right? But he said he'd do that with mass drivers, and you have to then move your production. In order to get that production on the moon, you need to use mass drivers because I'm not going to use fuel anymore. That's why I went to mass production. I do mining on the moon. And the reason you need to have, in the big picture, fabs built by Tesla, going from the Samsung partnership, TMC, make your own, is that they must master that so they can build and move fabs to the moon in order to go another 100x up, that order to magnitude up. So these things are decisions that are not like he's whimsically choosing to do it. It's like the math and the economic supply chain force these decisions in order to keep growing.
Okay.
So that's basically what that is. Go ahead.
Chris, would you agree?
I have a different slant on this, and that is that I think we're perhaps looking at the wrong elements of the limiting factors. So, Brian has a conversation that says, hey, look, as Elon has said, Starship will take care of putting it in orbit. And that's basically $10 a kilo. The rest of the logistics, whether it sucks up every, gram of methane that the US uses or not, theoretically, that's not the issue, right? So the issue, one of the things that I was working on was looking at the whole area of autonomous production, because this is ultimately the math of autonomous production is what we're discussing here. So we did applications of, we ran a lot of AI simulators that included all kinds of simulations for PV cells, for storage, for other components that looked at the solar energy as a product that you'd want to design and have AI build. And in this context, one of the things that Brian had said earlier was, that the V3 starships or Starlink is like 30 kilowatts. And we're suggesting that for logistics sake, we should say tens of megawatts is minimum system size. So you've got StarCloud at 40, but that there's this unit, 10 megawatts of putting solar out there, and that the application of Wright's law from PV cells to batteries to connectivity to systems, whatever would be involved in autonomous manufacturing, and this is Tesla and SpaceX's expertise, you'd basically apply and say, how much can I manufacture of these components that I'm going to need? And also, I think it's, when you look at it in this way, the classic ISRO mentality, the O'Neill concept, is fundamentally flawed. And, it's not that, it seems like you can't criticize O'Neill for in the 70s going at $10,000 a kilo, we got to mine the moon and do all of this other stuff. But I present the other side of this, which is the one thing that is unique about Earth is you already have existing fabs that can be scaled up with infrastructure. You can double or triple or quintuple them in order to get them going. You don't necessarily have to go to the moon.
Right.
And in this context,
but Chris, there are also problems with getting the licenses. You've got problems with generating enough energy for those fabs. You've got problems with water management and sourcing the water and all of that, which is, I think, one of the reasons
Understood.
why he's talking about space AI. data centers.
Understood. But what I'm talking about is there's a unique spark on the planet, which is existing human capacity to build the things that we want to build. Elon can walk down to the plant at Samsung and go, hey, let's walk the line. And that's, you know, you're not going to do that on the moon until a decade away, more so, right? So for the purpose of this conversation, you go, well, that's, you know, pie in the sky kinds of conversation about going to the moon. And, you know, what I think the context of that was really more the Kardashev conversation that says once you start ramping this up, then, you know, that is the ultimate limiting factor here. It's not the chips and how rapidly they're done.
Yeah.
So that's why I think I'd said to you in the green room, for me, one of the things, and maybe I'm skipping ahead, was astounding when I did my research, is that Starlink's solar panels cost $100 a watt, and they are apparently a breakthrough because most of these things are $200 to $500 a watt. And there's 3 talking points here. They say it's that expensive because we need to make them radiation hardened, thermal cycling, and the radiator challenges of emitting in outer space, radiative cooling, right? So even Elon, he just off the cuff, oh, we'll just have to deal with the radiation. And the interesting thing I mentioned, StarCloud, is they've split their team into 2 groups. The first group are the people that deal with the, you know, the panels and the efficiencies of the PV, and the other group is the group that says, oh, we've got the radiators. And so we looked at this and said the fundamental first principles engineering challenge we have is you get 1,350 watts per square meter in orbit at 25% efficiency. Those are, you know, 75% is excess heat. So you know, one of the things that I put in my slide, but I'll say it because it's easier, is we need to theoretically get the energy efficiency from 25% to 95%. And that means that you're primarily harvesting thermal, right? So this is the missing element, is that there's a technical challenge of building space radiators.
Yeah. And
that.
Yeah, exactly.
My point is I need to question some of your Starlink numbers on cost and on other factors. So one is my understanding of V2 Mini costs is that they are well under $1 million for that, and that's for the 28 kilowatts. The V3 design is for 68 kilowatts, and I think that they will increase that for the AI version of it, and that the V3 costs I've heard were 1.2 million for, and that would include everything, mainly communication stuff. And I think
the costs come from Grok, Brian. I literally just asked Grok, and it gave me also the reasons. There's a long report that I have here, and you know, basically there's things about how it's only 25% efficiency, yada yada yada, but whatever the numbers are, I got them from Grok.
Okay, so my belief is that they will put up less modified solar, accept the degradation that they'll have, launch them more, so they'll over allocate. Like if I'm going to need 70% of the power for my chips, I'll over allocate 30% for the degradation in order to address the cost aspect of it. So they'll send up more on modified or less modified solar in order to get the cost down. So then I think that that they'll be making a factory, like the largest on-the-ground solar factory production in China, produces 50 gigawatts per year, and that had a capital cost of about like $9 billion, right? So just rounded to $10 billion for that. So then they will make that volume thing and send up less modified. So they, instead of going to making it more efficient, they'll go with more as is and accept the losses of the thing. So going on a different path than what you're suggesting. But let's
I
debate
would-
that technical point later. Go ahead. Okay.
Well, I thought I was going to do it now. I actually agree with you.
Okay, go now. Okay.
Because, I mean, I know, Rodin, did you want to show the thing beforehand?
Yeah, but just complete your thought, and I
Okay.
will
So-
I will then play out the soundbite.
To exactly that point, one of the things that Starlink had already done is say, instead of using gas 33% PVs, we're using 25% silicon. And that's even the approach that I'm looking at, and basically saying our first solution is to say, go to the terrestrial floor. Like they do things like shave the cells so that they're slightly thinner for space. I'm like, no, right off the line, stick it on a rocket, put it in orbit, right? Maybe some hardening issues is fine, but the Grok was telling me that the challenge is they go, well, we need 5 years out of this because it's in space. So I'm like, no, change the approach, make the arrays and the radiators and all of that be a lattice infrastructure, whatever it is, and put in replaceable tiles and assume, oh, it's in space, it lasted a year, boom, it's gone, and then have an automated system to just put in a new chip, because the tiles themselves are like $1 retail right now, the ones that I'm looking at, or less, right? And they're generating 11 watts. And then you apply Wright's law to say, add in these, space hardiness, but don't go crazy like they're doing now, and address the thermal issues with the structure itself and active cooling, so on and so forth, so that the cells think they're sitting on Earth in a lovely, bath, right? Address it as an infrastructure. And in that way, the economic benefits of continually cranking out lower and lower PV cells works for terrestrial, works for space, and that's where you get the exponential leverage. So we'll be able to basically say, oh, it's a penny instead of 20, 30 cents that it is today. And the fact that we want to put a gigawatt in orbit or a terawatt is actually the driver that makes Wright's law drive the price of solar to literally zero. And I'll end there because I passed my 2 minutes.
Let me just quickly play out the soundbite, because then we can take this discussion forward.
Fine.
And this is about 3.5 minutes long, so bear with me. I'll stop along the way and we can discuss what Elon and Jensen are talking about.
AI in space. Is that possible?
The way to think of AI in space is that in order to achieve any meaningful percentage of a Kardashev 2 scale civilization, where you're using even a millionth of the sun's energy, you must have solar-powered AI satellites in deep space. So that once you realize, once you think in terms of a Kardashev 2 scale civilization, which is what percentage of the sun's energy are you turning into useful work, then it becomes obvious that space is overwhelmingly what matters. Overwhelmingly, the sun only receives roughly 1/2 billionth of the Earth only receives roughly 1/2 billionth of the sun's energy. So if you want to have something that is, say, 1 million times more energy than Earth could possibly produce, you must go into space. This is where it's kind of handy to have a space company, I guess. Sell the book.
Easier to cool chips in space, too.
Yeah.
Okay, before we get to the whole discussion about cooling chips in space, Chris, you were talking about Kardashev 1 and 2 level civilizations. Do you think this is achievable within the next 5 to 10 years, or are we looking at a longer timeline? Chris?
I have some modeling numbers here that have it at, let's say it's closer to 2040. But here's the thing, to the point of the earlier conversation, it's going to be interest constrained and hence fiscally bound.
Explain that.
Well, it's as long as people continue to say there's this exponential return on adding intelligence, and that this is, and as a singularitarian, I agree with the concept. But, just like people are talking about an AI bubble right now, and, people will worry when the lights go out in their houses because the AI is sucking up all the energy, right? So the key is, not just, well, maybe I'll put it this way. What percentage of planetary GDP are we willing to put into solar energy? Never mind AI. So, I was a member of the Carbon Removal X Prize. So Elon put up $100 million. And he basically was talking about, well, for 1 or 2% of GDP, if we get a scalable solution that addresses climate change and CO2 removal, yada, 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 then that's addressing an externality, so on and so forth. In the same way, for us to get to even before a K1 civilization, to get to the point where we've got tens of terawatts in orbit, along the road to the Dyson sphere that's currently being discussed, we need to drop at least 3 to 4 orders of magnitude, maybe 5, in our production costs. So that's what we're seeing on the surface here is from PVs to AI chips to whatever, until ultimately what is in space is a floating array that has embedded AI in it, and you can go down that road. But that's the product that you scale, like the version 3 of all of this, not just, hey, we're going to grab some.
So you're
NVIDIA
saying it's closer to 2040?
Yeah.
Okay.
So
here's my question to you both now. Let's
Before it
not
gets
forget
to
the
that.
geopolitics of it. Hang on. Let's not forget the geopolitics of it. What is an acceptable cost for the US to maintain dominance over China? Because when it comes to building AI data centers and also chip fabs on Earth, it's far easier, or even solar powered solar manufacturing units. It's a lot easier to do that in China because you don't have to deal with environmental concerns. The CCP can just pump in money and do that. That's very different in the United States. You have to jump through legal loopholes. You've got environmental costs. You've got a lot of problems. How are we discounting the geopolitics of it? And what is a cost that is acceptable enough for the US / SpaceX / Tesla to maintain dominance?
So let me go first here. One is I disagree about the cost and the time to scale. I believe that getting to 100 gigawatts cumulative in space with modified version 3 satellites, Starlink satellites, is possible and is cost effective by 2030 at the earliest, 2032 at the latest, which is different from the 2040 timeframe that was discussed. So here's why. One is the statement that solar is $100 per watt for SpaceX, I think is wrong. So the $1.2 million rough estimate for version 3, right, is, I think, at most $10 per watt, not $100 per watt. It's $10 per watt.
Let's go
Why?
with $10 per watt, because even if we discuss this as disposable, right, we use that model and just go, okay, we have a budget at $10 per watt for discussion purposes. It makes it much easier than arguing the whole point. I'll concede that point, because otherwise the economics is just too crazy. It's $100 trillion to put a terawatt in space, but at 10 trillion for a terawatt, is that still useful? That's why I'm also going, well, no, you need to model at least no more than $1 a watt finished product in orbit, operational, so that a terawatt is $1 trillion. There's an acceptability technology, right? So we can just say there's a concern about economics that will be addressed by basically going from the production lines and putting them into orbit and then just replacing them on space.
Okay,
right.
So I would say that for 100 gigawatts, right, that if you get down to $1 trillion for launch and energy, right? So basically $10 billion per gigawatt, right? That is the cost, the Earth-based cost, roughly. That if I have to make new natural gas and new other things, that is the crossover point at $1 trillion, right? And you can go up to double that or even triple or quadruple that, $2 trillion, $4 trillion, because the there is no other way. Like those ground options at the $10 to $20 billion per gigawatt on the ground go away, because you're already waiting in line for your natural gas plant. The nuclear, I'm lucky to make 8 in the West nuclear power plants by 2035, 8 gigawatts. So then if I'm looking to do, say, ballpark, the 300 gigawatts per year in the 2030s, right? That's 3 terawatts, 3,000 gigawatts,
Well,
right? So then there's no other option there. So either I do not make 2,900 gigawatts of power, or I need to then pay more for. So the budget goes from 60% chips and 10% or 5% energy to 30% energy, and I still then can use the chips. So then I can go up 4 times in cost, and it's still, or even like more. I can go up like 10. If like there's no other way to power it, I'm gonna take the solar, shove it into my Starship, launch it, and then accept the cost. To your point, at a certain point, the economics break. At what point, if in my total, yeah, go ahead.
but there's Brian, let me interrupt, because there's a bunch of things here that I didn't even realize that I didn't say in my off the cuff remarks. So I went back and I looked at my notes and what I was modeling. So I'd modeled this to say, could we be producing 1 terawatt per year in 2033? Okay, that's what all of this stuff. So basically, that means 2032, 500 gigawatts. What I did is said from 2027, we start at 10 megawatts, which is still, if you think, okay, show me 1,000 Starship or 1,000 Starlinks in a cohesive array, put something up, a quarter the size of Star Code. That's a proof of concept, in my opinion, right? 10 megawatts. And then I said double every year, or no, 10x every year throughout to 2030, 5x 2031, 2x 2032, and 2033. So if I just looked at this from the logistics of humans moving that fast and scaling, and a lot of the things that Tesla goes through in the autonomous production, all the conversations that we had about that, and you apply it to solar cell manufacturing and components and systems together, it is really like the Apollo program in terms of systemic scope. So, as I go through these things and you go, well, year 1 in 2027, you might have done 1 10 megawatt collector, but by the time you hit 2033, you built 33,000 of them. So, it's really what I'm trying to describe is to say there's a 1,000-fold increase from today on what we're trying to cram into a decade, let's say, right? Is it possible? Well, to Elon's point about Tesla and its own future, if execution's perfect.
I don't think it's a question of whether it is possible as much as, and you made a very apt comparison to the Apollo programs. Why did the Apollo programs come into existence, right? Because the US felt it needed to dominate the space race, right? And this is akin to that. This is the AI race. And America has realized that there are problems when it comes to building AI data centers, when it comes to manufacturing chips, and even when it comes to the realities of the Trump administration's decisions on where to focus on energy, right? So it's an existential question and an existential problem, which is why I come back to the question, a very quick response from the both of you gentlemen. Is this really a question of opportunity cost? Can the US afford to fall behind China? And therefore space is the only way to go?
So as I said, space is the only way to go. But let me just go to the point of the starting point of like what we're scaling out. So we already have 200 megawatts in the Starlink satellites in orbit now. So the 200 megawatts is there. They're distributed, not in 9,000 units, but they are up there now, which is
what is Starlink's annual production capabilities, and add into that what is Solar City's capabilities to build these cells so that Tesla could self-supply.
So currently, the SpaceX Starlink production is 3,000 Starlink per year at about the
No,
28 kilo.
megawatts. Yeah. What's the math?
I'm converting to megawatts. I'm converting to megawatts. So 3,000 times 28, which is basically 90 megawatts per year right now.
So say
90
100.
megawatts per year. Say 100, right? And the scaling up of the V3 that they're planning to launch in 2 years, right, will go to 10,000 to 20,000 V3s at 70 kilowatts, maybe 100 kilowatts per unit. Let's do a simpler math. Let's call it 20,000 times 100 kilowatts. So basically, you're at 2 gigawatts of production per year in 2 years. That they
So
already have the
28,
plant
right?
by
But
27,
28.
28. Yes.
Yeah, we'll say 28 because this year
Let's
is
go to
not.
28. Fine. And give a year. Yeah.
Right. So
So two,
that's 2 gigawatts of cells that would be devoted to this. Is
no.
that
This is
because even if that's
no.
for Starlink satellites,
Hmm.
as we've discussed before, people are going to go, well, why don't we put some processors in those damn things?
Right. So this is already the plan. Going to 2 gigawatts. So a 20x step up from the 100 megawatts to 2 gigawatts in 2-3 years was already the plan before we started talking about AI data centers. Right? Before we talk about AI data centers in space, he was already doing this for the communication satellites, high-speed internet, direct to cell phone. Right? So a 20x step up in 3 years was already the plan. And then I'm saying that the existing large super factory in China, a facility of a few buildings that produces 50 gigawatts of solar, is the next step up, like 50 gigawatts, multiple units, like get to 100 gigawatts per year by making the space equivalent, minimally modified, of the existing solar cells at the scale of existing China plants. Each one, each of their gigafactories of solar is making 50 gigawatts. So going from the 2028 2 gigawatts per year, in 2030, having that other plant built up to make 100 gigawatts per year, that solves the production levels and the production costs of the solar that they're making. So they're going to basically, like we kept saying, how come Tesla and Solar City don't make the 100, like the 700 gigawatts per year of nameplate solar that China does? It's because now we're going to make 100 gigawatts by 2030. So still, 10, 15% what China will have but this is all solar only going to space, not on the ground. And so it'll be another step up from the 2 to 100, so another 50. So a 20 step up already planned to put V3s, another step up 20 to 50 in 3 years, 2 years, 3 years for this new facility, and this new CapEx spend of about 20, if they can match China, $20 billion, if it costs double, 40 billion, that level of difference is meaningless in the trillion-dollar step we're talking about. So in terms of like actual factory units, this is the production of going from 100 megawatts per year, 2 gigawatts per year already planned. They've already got commitments. The factories are going. They're making version 3s. They're already ramping that factory. It's already happening. And then they're going to set up a new factory, this next level of this 3-year thing, to go to the new goal of 100 gigawatts. So Elon pulling out 100 gigawatts per year, he didn't like pull it out of his butt and say, it's going to be 100 gigawatts. It's like he's saying, I'm talking to my team of 50, 100 guys, and then we're doing acquisition of locations. We're buying equipment to do this production, and we know exactly the cells we're making, similar to the ones we're doing for the V3 satellites that we already have in production, and we're going to scale it up that next level. So it's
Okay.
like
I want to get back to the soundbite and continue with that.
Ships in space. Yeah.
Yes, there's definitely no water in space, so you're going to have to do something that doesn't involve water.
Just hang out.
Well, you just got to radiate.
That's right.
Like the cost effectiveness of AI in space will be overwhelmingly better than AI on the ground. So far, long before you exhaust potential energy sources on Earth, long before, meaning like I think even perhaps in the 4 or 5 year time frame, the lowest cost way to do AI compute will be with solar-powered AI satellites. I'd say not more than 5 years from now.
So very clearly, he's talking about a different constellation here that's different from Starlink, right? Let me just get that.
No, I think he's talking about the same thing as Starlink. That
Okay.
he's talking. So
There's a
the V3
merger.
Yeah,
There's
yeah,
a
the
merger.
So instead of putting communication equipment in there, I'm going to put in the AI chips. So
Okay.
Or
that's
no,
And that
no,
starts
no,
with
no,
V3.
no. In addition, it'll be
well,
every satellite is a Starlink satellite with communications and AI on board.
Okay.
they'll
And this
reduce.
starts with
I'm going to
V3
say
or V4?
I think it will be mainly V3, but it could become a V4. There'll be V3 and V4 won't be that different. It could be double in scale. But so the unit of
And
size we're
which
talking about
chip
for
would
V3.
that be? Would it be AI 6 or would it be possible to start it with AI 5? Because we know AI 5 is coming in 26, AI 6 probably 27, 2027.
No, 5 is not supposed to ship until 27, end of 27.
27 in volume. Yeah. So AI5
Right.
doesn't go
Volume,
in
but it
20
starts in
volume.
But assume they've got access to the early ones, and that this is not going to be later than 5. And
Yeah.
to Brian's, what Brian had said earlier, it was a good point that you made about if they in fact have access to 2 gigawatts of production by 28, then you notice that what Elon had said is within 5 years, which is 2030-ish, that you'd be looking at 100 gigawatts. So basically that's the curve that you have to navigate between 28 and 30 to go from 2 to 100. That is likely going to require more than SpaceX or Tesla. And the other thing is that they're already using like Chinese cells. They're using American cells. They're using off-the-shelf cells. So, I think they do the same thing as they would do with batteries, which is we have to manufacture our own, great, but take them as they come and let's get as many as we can into orbit.
Okay, so to your point about the cells, he says something interesting, which I want to just play out. Let's go back to the soundbite.
And just look at the supercomputers we're building together. Let's say each one of the racks is 2 tons. Out of that 2 tons, 1.95 of it is probably for cooling.
Right.
Just
Yeah.
imagine how tiny that little supercomputer is, right? Each one of these GB300 racks will just be a little tiny thing.
And
Okay, so a quick clarification here. I was a bit confused what Jensen meant. Are these GB300s going to be the first load on as part of this this AI constellation, or is it going to be Tesla's own chips?
The prototype test scaling, which will be significant, to Chris's point, that if I'm loading initially, when I get my Starship going, and can spare some launches, I'm saying 10 megawatts, which would be about 5,000 chips, right? At the 2 kilowatt level, they would be NVIDIA B300s because I wouldn't have any other chips next year or even in volume the year after that. So the first
so
2
we
3
could
years.
see this starting in the second half of 2026 with B300s.
Right, but this is for the early phase and for the unique position of Starlink. The early, more expensive versions, the first 5,000, 10,000, whatever chips, they would use that for content distribution and for AI nodes that would integrate with Starlink. So then they would reduce their dependence on ground stations by using that. So you'd be able to improve some performance with lower latency communication to get AI answers. So they will upgrade the existing Starlink network to have extra intelligence and memory and that kind of stuff. It's just like on the ground in the internet phase, you built out all this fiber, and then you had companies like Akamai and F5 or whatever it was that did this network. They will then move from ground stations up to use that less, have it directly there. It will reduce latency, it will improve certain other performance and that kind of thing. They already have chips up there, which are about 5% the power of a H100. Those are AMD Versal chips. They use them for calculations of beam forming. So they're using it for communications and efficiency in communications. So there are ways to add more communication, more compute, and more memory to improve an existing business that is generating $10 billion per year now, and will by 2026, 2027 be generating $50 billion per year. So if I get 20% more performance, that's worth $20 billion, right? So there's or $10 billion. So there's economic value that only SpaceX can currently have because they already have a money generating communication network up there.
Right. Understood. Okay.
If-
Let's
if
continue
I-
with that.
If I can add to,
Yeah.
if I can just add briefly, one of the conversations that StarCloud was having that basically reinforces the idea that Starlink, the communications satellite, will now be an intelligence node, part of the Orbital intelligence network. That's really it. Is that he said StarCloud's first commercial business is providing AI services to other satellites, so that you'd have various satellites that wouldn't have to beam ground side, and they basically could just say, oh, this is a forest fire, this is whatever the case may be. And that's the predominant business to service the space community.
Right. Cool. Okay, let's continue with the soundbite.
Just electricity generation is already becoming a challenge. So if you start doing any kind of scaling for both electricity generation and cooling, you realize, okay, space is incredibly compelling. Like, let's say you wanted to do, I don't know, 200 or 300 gigawatts per year of AI compute. Yeah. It's very difficult to do that on Earth. The U.S. average electricity usage, last time I checked, was around 460 gigawatts per year average usage. So something like, say, at 300, if you're doing 300 gigawatts a year, that would be like 2/3 of U.S. electricity production per year. Yeah. There's no way you're building power plants at that level. And then if you take it up to, say, a terawatt per year, impossible. Yeah. Like, you have to do that in space. There just is no way to do a terawatt per year on Earth. And in space, you've got continuous solar. You've got you actually don't need batteries because it's always sunny in space.
That's right, exactly.
And the solar panels actually become cheaper because you don't need glass or framing, and the cooling is just radiative. So that's why I think
That's the dream.
Yes,
That's the dream.
All right. So there you have it.
And that's where they buried the lead, both of them.
Yeah.
Right? Is the number one first principles problem for all AI chips is cooling.
Cooling. Yeah.
And the misconception that the audience has that space is cold, so it's pretty easy. They don't understand what radiative cooling is and the limitations.
Yeah. And I think Jensen made a valid point there when he said, when you look at, Brian, we've discussed this in the past, and you put up a slide for us where we look at those 4 square kilometer size, structures. 95% of that mass and more perhaps would be the infrastructure needed to capture solar energy and then radiate heat out to cool the chips, right? I think that is something that people need to wrap their heads around.
Right, and the solar panels they have there, typically on the back of them, of that structure, is where the radiative cooling part is. So the power comes into the solar cells, and then it goes into whatever you're powering, communications or compute, and then it comes back out along the back of it to radiate the heat off of it. But that problem has been solved at the 28 kilowatt level and it's actually at the 200 kilowatt level or 40 kilowatt level for the space station. But for these mass-produced under $1 million Starlink satellites, I think it may be only at $300,000, $400,000 for the V2 minis, right? They have this solved at that level. And the thing is, people say, well, I'm going to power chips, AI chips instead of communications. Pulling in electricity, I got to get rid of all of that thermal because the electricity becomes thermal. Even if I didn't do it to it, I just had to I'm sucking in 28 kilowatts. I have it. I need to then radiate it out, right? So then in some ways it's an engineering thing of what I'm powering and cooling, but then that raw number, 28 kilowatts for the V2, 68 for the V3, maybe 100 for a modified V3. These are things that they already have and do and can scale up. So when Elon says, okay, I don't have to have these other weight things for it, he's already been doing that at that 200 megawatt level and can do it at the 2 gigawatt level. So it's
a matter of scaling up.
It's a matter of scaling up, but not from nothing. It's like I don't have to come up with my solution. I have to just use the same solution or slightly improve it to do what I need to do.
Okay, Brian, you've got some slides for us, and Chris, you have some slides as well. Let me quickly start with Brian's in alphabetical order. Bring this onto screen, and if you can take us through this very quickly, please.
Yeah. So I'm just saying that the inevitability of this means. So there's been some slides by and Evan. Benedict Evan Benedict from A16Z, a big venture capital company with billions of dollars deployed every year. So he says AI eats the world. So that's a really good thing, and we don't go over all of it, but basically he makes a very strong case about how the tech companies need to take over all the energy and other things on Earth, and that's rapidly happening. So here we go to TSMC. In April, they gave a little talk, their technical talk, talking about what they see, how they see their chips growing. The green line on bottom of this chart is what to look at. Data center AI accelerators, which are the GPUs, 5 million per year, 2030, and then going to 50 million per year. Sorry, 2023, going to 50 million per year, 2030. So that at 2 kilowatts for each B200 is about 100 gigawatts per year. So again, the 100 gigawatts per year that Elon was talking about, you see it here again, about 100 gigawatts per year, just from TSMC. And TSMC will have about 70% of the market, 60% of the market. So then you almost double that to get to 200 gigawatts per year. Go to the next slide.
I'm going to rush through these slides, so let's spend about a minute on them.
Yeah. Okay, so then that Benedict Evans says that NVIDIA and TSMC can't keep up. Right. So that goes to why does Elon need to get his own chips and stuff like that? Is because they can't keep up. He has showing how NVIDIA is shooting up to $60 billion per quarter, and then TSMC scaling up as well. So the scaling up this curve is something that those two companies can't keep up with. So the 200 gigawatts per year I just previously talked about, not enough. They want even more chips, more energy. Next slide. So then all the electricity that we're adding in the world last 12 months is less than 800 terawatts. If you that top bar on the left, less than 800 terawatt hours per year. What does that 800 terawatt hours per year mean? When you have 100 gigawatts from solar, from nuclear, whatever, and you're generating power all the time, there's 8,680 hours in a year. You're looking at 860 terawatt hours per year. So the 100 gigawatts per year that Elon's talking about is more than the entire world new addition of energy. So no one previously was saying within 5 years or 7 years, I will be able to add the entire world's energy from ground-based solar, wind, nuclear, like that, by putting it up there. And by making 2 existing solar factories that the equivalent of those 4 ground-based that China has to get to the 100 gigawatts, that 100 gigawatts on Earth would only generate the equivalent of 80 terawatt hours per year, because by putting it in space, 24 hours, double the intensity, 5 times the time. So it becomes each of those things becomes like nuclear power plant levels of capacity of constant generation. So that's the advantage of like once I move it up there, it's 10 times better. So to the last point, if I want to wrap up in a couple of minutes here, is that using the existing factory lines to do it, I think is better. Yeah, this goes to the energy of the problem. Elon said it. This is just a slide showing that the problem. So before we get on to the next step, I don't think we need to go to any more of our slides. Is that
no? I think you had an important slide about the NVIDIA production capacity.
Okay, go.
So I think that's very important to this entire discussion. Here we go.
Yeah.
So this is to the point that Elon is making about the terafabs, right? And I think this is important to kind of explain to people out there that there is a limiting factor, and that limiting factor also is chip production right now.
Right. Chip production is a limiting factor. It's the only limiting factor if you have abundant energy, because right now energy.
It's the same chip. In both cases, you're looking at silicon. One's going to AI, and the other is a PV.
I know that, but the issue is that them being TSMC being able to do 50 million chips is abundant chips. If I cannot power more than 50 gigawatts of chip, then I only need 25 million chips, right? So if I take off the limit on the power and go to 200 gigawatts, a terawatt, at a terawatt, I need 500 million chips, right? Or I need even a smaller power usage. I need 1 billion chips.
Yeah, but let's be more practical. So a square meter is 1,300 watts. So say a kilowatt, that's one chip. So a square meter of solar is one chip. What's the likelihood that square meter of solar is going to be even an infinitesimal fraction of either the production limits or the cost compared to the AI chip that is operating from that solar? Like, it's not going to be solar that it is still like 99.x% constrained on the AI, the ability to convert silicon into AI chips. Like, to your point. NVIDIA's fab capability, terafabs.
Yeah. Okay, so I think the solar can be built. The investment cycle and the revenue generation everyone has, all these, we're growing fast. All of that comes to a stop in 2029, 2031, because we hit power limits on the ground. If we don't go to solar, go to space, then this growth stops for most of the entire decade, right? Or even longer. So that goes to space being the only solution. So then if I need to adjust my cost thing initially to get more power up there, then I just have to do it. And when he was saying, okay, getting 200, 300 gigawatts per year, if some of it's NVIDIA chips, because they're doing things as fast as they can, so they will be still using NVIDIA chips, and they'll also be using Tesla chips, and they're using Google chips. So then we're using all the chips and we're getting them all powered.
Get their hands on.
Whatever
they can get their hands on, right?
Right.
And I think it's important to also at this point talk about the AI bubble very quickly, because it's kind of one of the biggest discussion points out there. Is it justified? Are the fears around the AI bubble justified when you look at the sheer amount of demand?
Not according to Jensen.
Yeah, not according to Jensen, yeah.
So
not according to Elon either.
So go down those slides. There's a slide on that. So go next slide, $3 trillion. Next slide.
More accurately, not according to his financial report.
Okay, here we go. Value to capture. So advertising is $1 trillion per year. Okay. So the US part, the big hyperscalers, is almost half of that total amount, right? And Meta and XAI and stuff have talked about getting 20% more advertising efficiency, and more advertised dollars by using AI to do the advertising. So that's like in the past. So then, even for Meta alone, they have closing in on $200 billion worth of advertising. So if I got 20% more, that's $40 billion. right? And if Google Search and XAI all have it, then we're talking about $100, $200 billion from advertising AI efficiency, right? So that already, if I'm spending $400 billion, $200 billion giving from advertising is already a big value. The other big category is $5 trillion per year for IT, software and data centers and all that kind of stuff. So if we convert that over to an AI version and get 20%, 40% more efficiency, then we're talking about $2 trillion. So
and let's not forget the likes of Salesforce, the likes of Klarna, Amazon, etc. So you're seeing AI being deployed and hitting the bottom line and the top line really across sectors. So this is very different from the dot-com bubble.
Right. Okay, so that's the slide,
also you
the non-AI bubble,
And also, I'd suggest you have to look at this from the demand side. So when people talk about 1 billion times more inference demand, and that we're discussing creating an orbital intelligence that manages all intelligent machines on the planet, shades of the board, but still, that's what we're discussing.
Right. So I think that the number of chips and the power levels, especially if the scaling happens over this next 5-6 years, where we go from 200 to 2 gigawatts.
What is the biggest challenge according to you?
Chips is not a problem. Everyone's producing a lot of chips. If Tesla's chips aren't ready, they'll launch NVIDIA chips. The solar, the part that Chris was talking about, I don't think that's a problem. They'll be at 2 gigawatts from plans they already have, and then they'll go to the 100 gigawatts by 2030. Maybe it's 2 years late, 2032.
How much does SolarCity play a role in this? How much is the solar manufacturing capacity?
And you also have to define, Royden, what you mean by this. What's the metric? What's the goal? A terawatt?
The 100 gigawatts per year. Once you're at 100 gigawatts per year, then that's, they only have room for another 4x, 5x to 500 gigawatts. Elon says that you're hitting the 500 gigawatt limit there. So you'll hit limits there. So 100 gigawatts is you're really there anyway. And it is, that 100 gigawatts would be 8,500 terawatt hours per year. It's a China of electrical power every year.
Each year.
Right.
Yeah.
Each year. Sorry. At the 100 gigawatts, it's at the one for the decade. It'd be the 8,500, right? If you go up to higher levels, then it's multiples of that for each decade. Because you'd add the terawatt by 100 gigawatts per year. If you go to 300 gigawatts, then you add 3 terawatts, and that would be 3 times China's level. So the challenges is launch. So in order to do this, you must scale launch to 10,000, 30,000 levels. I need to get all this fuel into it, and the solar power plants and the factory satellite production. I'm going to have 10, 20, however many launch facilities. Each one will launch 1,000, 2,000 launches per year, right?
Yeah.
And I need to have...
And all of that is dependent on Starship, until and unless you can scale up Starship.
Yeah, Starship is the only way you do this.
Yeah.
Right. Starship is the only way you do this. And so I would have factories around my spaceport, and I'm going to be building the satellites, building the solar. And because I'm moving so much stuff, they're going to come into a center thing, and then there'll be starships lined up. So they're going to be launching 5 times, 10 times a day, right? So that means I have new boosters, new things stacked. So if I'm having 3 days of stuff stacked, ready to go, I could have 30 starships fully stacked in a line where they're stacked, and then I load in 200 tons of satellite into it.
So are you saying that you see most of these factories now located in Texas?
No, I have to have more.
Right, he's describing a starport. As we
multiple
discussed,
starports.
They're in the marine shipyards. So what we're seeing at Starbase is literally you do that everywhere around the world, and you have all these starports.
Or distributed alien dreadnoughts across the planet.
Right. Sure. So I need 10 to 20 or more starports at each place. Each one is like a star base, but on top of that, I also have a gigafactory for my solar, a gigafactory for my satellites, and I have factories or handling of 20 to 40 fully loaded starships off each one, and I'm lining up and loading it. So I have to have massive facilities for loading this stuff in. It's like the giant container ship loading. I'm
That's
loading
exactly what
all
it's like.
kinds of.
Yeah.
He's
So
describing a starport in our automated operations, Brian. You really
right,
need to go back and look at our proposals because this is all there,
right,
man.
All right.
right.
So let's talk about cargo ship level 1 and 2. Chris, you've got a few slides. Let me just pull them up one by one on stage. So the Stellar Harvester, take us through it.
Yeah, well, this is not so much the Kardashev. It's reframing a lot of what we already discussed. The first is these are the concerns that you have. We've discussed having to scale up by 500 times or 1,000 times the area to get roughly to a 10 megawatt-ish kind of scenario, just from a practical logistics. We've also discussed that under economics, that we want to use Wright's law to pay no more than a penny a watt for PV. Let's just put it that way. That's the limiting factor that we're dealing with right now. And if it's 20, 30 cents, we need to get a 10, 20-fold reduction in terrestrial PV cells and that technology. Now, this gets to the third part of it, which is the critical part, which is the efficiency of those cells, as well as the cost. This is the chart that we discussed before that basically said if it was $100, you want to be able to, over time, get to the point where it's absolutely free. This is what you're seeing as Wright's law, which is how autonomous factories generate their costs and get continually reduced costs. So as you see, you get around 140,000 gigawatts, you start seeing all of the cells come down. That's basically let the planet that already produces PV cells continue riding the same solar train it's been doing for a decade. But the second point of this is that we talk about this being a solar energy harvester, and that at 25%, you've got a 10 megawatt facility, but we basically say as you go to 100% by doing infrared or other techniques, we're focused purely on visible light, and ultimately the radiative cooling and thermal management issue are all part of the same thing, which is how to turn heat into compute. And in that context, we've been looking at this and going, well, why not do things like thermocouples in addition to PV, right? So that there's that same technology, but then secondarily, you look at Xtropic's thermocomputer and the fact that you could use the waste heat being radiated out as a compute in and of itself, and apparently that's like 10,000 times more efficient. So, without going too far off the deep end, if you're looking for maybe the next gen of what this should be in space, I'm suggesting you ultimately want to create a black hole that is 100% efficient, or as close as you can get to absorbing all the energy, and then that ultimately leads to storage.
Is
and
that the Matryoshka brain that you're talking about? Everybody's
that,
talking about.
yeah, and thank you for bringing that up. So, I put that in the chat, and I'd mentioned that in the previous slide. Bradbury in the early 90s had taken the Dyson sphere concept that Elon's talking about, and it extended to this thing called a Matryoshka brain, which is where you have concentric circles. The innermost circle, of course, gets the visible light like a Dyson sphere. And then as you go out, you have larger and larger spheres, and they're basically computronium on the outside at higher energy levels. That's literally how you go down the entropic chain and you turn entropy into intelligence. Very cool concept. So, partly just to put this in a one of the things I said before was to make these cells work, we want to be able to do disposable cells and batteries, and so we're calling this a stellar tile. And the idea is that that's a device that may or may not contain AI in it, but that it becomes mounted on all of these large arrays and basically set it out in the sun and forget it. And that if you think of the backside, the dark side of this, the idea of being able to embed thermocouples and other technology to implement a Matryoshka brain on a stellar tile, through metamaterials, that kind of thing. That's the part that I kind of found was cool.
Well, for me, the question is really the timeline, because as Elon says, if it doesn't violate the laws of physics, it's not only plausible, but it's possible. But it's a question of, again, how much money, how much energy, and how much of resources can you deploy in the quickest timeline possible. It all just boils down to timeline.
Well, maybe in that context, sorry if I interrupted, partly the question is that, sizing. Like my sense is, are we going to see somebody take a crack at a 10 gigawatt one? Sure. Everybody's going to try that. Is it going to go past that? Like that's a second question here. Does it scale to be terawatt scale?
What do you think, Brian?
So the scaling that we're talking about, like 100 gigawatts per year, 200 gigawatts per year, I'm saying basically it's with B3s. And in order to get to those production levels, you have to lock in the technology, because I'm going to make giant factories that will produce it. So basically the changes of more efficient solar panels, do like that is a 10-year thing. It's just like I'm going to upgrade my my batteries in my car. Like we're still using lithium nickel when we switch to LFP. These technology changes are difficult at scale. So what Chris is describing is a end goal, which is something you want to achieve. But it will be, I think we can get to the 100 gigawatt scale, 200 gigawatt scale with what we already have, and that we will do it. It'll be having 30%, 50% losses on things is acceptable, because I can either do it at scale or I cannot. So it also goes to how we have.
Brian, what's your prediction for a 100 gigawatt single facility or owned by a single entity, right? By 2030.
So things have to go right for it to happen by 2030, cumulative, not 100 gigawatts per year, but cumulative. So over like really 28, 29, 30, 2030. So then probably it takes a year or two longer, 2031 to 2032, to get to the full at, and then you'd have 100 gigawatts per year, 2033, 2034. And it's basically all these factories, all these launch things scaling to do that. And then going up to the 200 to 400 gigawatts per year, as Elon described, would happen over the next few years.
Okay.
Can I ask both you gentlemen, how much of a threat is the presence or lack, either way, of an enabling political dispensation?
Well, like maybe I'll step in, because you've been talking about the geopolitical angle, and appreciate, given where you're located and your interest. If I step into that, there's clearly going to be a U.S. repatriation of PV and chip productions.
Right.
So what Trump is doing there is the fact that China is making so much more PV than the U.S. is problematic in this case from a national security perspective. So that's why I expect that you're going to see, and for all we know, Elon's talking to Trump about, hey, can I put a terafab in? What's the tax break? I mean, why not? Right? That ties into the geopolitics of it all. And I think that's, I don't want to go too far afield. You and I had discussed before, Royden, that, I view the Trump administration's desire to get into this tech as positive for the planet and for the US.
Yeah. But if come 2028, if you have the Democrats come back to power, is this going to continue?
So the building, I think, has to continue, because it's NVIDIA's growth, it's Google's growth, the entire tech industry. If they go from growing 40% per year, 30% per year to 5% or nothing, right? Then that would just slam the stock market. If growth stops, S&P 500, gets slammed, because you're pricing in growth. So if growth cannot happen, so it's a massive forcing function of like, it's like for Jensen, if this happens, he's selling 50 gigawatts, which is basically like 100 times what he's selling now or something, right? So either he goes to 100 times what he's selling now over the 2030s, or he doesn't, and like no growth, or maybe only double, right?
But it won't be
So
just Jensen, it would be AMD and everybody else, right?
There's maybe
everyone.
a way of maybe I'll suggest it this way. Even the Democrats can't prevent the singularity. And that's what this is all about.
Do the Democrats know that? That's the question.
They undoubtedly do not, because this is related to a lot of the psychological and sociological problems that come from the disruption of exponential technology. So, as we see wokeness and people on the left doing crazy things, and there is going to be on both sides of political ideology people who are not of sound mind, shall we say, in terms of logistics and actions. And we have to expect there's going to be a lot more of them coming our way. So, the thing that I would also look at is not just the national interest, and maybe this is encouraging, is this is driven by Silicon Valley and people like Elon that go, it's in our own commercial self-interest to have ASI. And so we're going to build it, and nobody's going to stop us, because we want to be prepared to get into the singularity. And so this is where every nation on earth and all kinds of politicians will be going, wait, I want to prevent you from doing this. Not possible, right? It doesn't matter who you vote in the office. It doesn't matter if they say, go out and destroy all the machines.
Yeah.
That's partly the beauty of somebody like Elon going, well, if I want to make a planetary infrastructure that is safe from the savages, put it in orbit, where it is beyond anyone's ability to do anything about.
Yeah.
Right?
The other thing is that at 100 gigawatts per year, I'm adding more than the entire oil industry in the United States every year. Right. So no one's standing in the way of that. And so that's the only way to do it. Right. And then in terms of geopolitics, 5 years at that level, and you've doubled U.S. power, and now the U.S., instead of being half of China, is now equal to China. In 10 years, they're at perhaps more power than China. The only people can say, "Oh, it's impossible for the U.S. to catch up for China in power." Again, this is the only way, and China will not have a Starship for like 20 years.
Brian, you bring up a super important point that we need to circle back on, and the discussions about, first of all, Tesla being a sustainable abundance company now. And that mantra, which shifts exactly this energy conversation. And many of the conversations that I've heard that basically say, once you go down the Tony Seba solar is free pathway, the stellar worlds model, that you're saying the thing that drives all economies, all civilizations, energy, is free and abundant. So that means no electricity bill for Americans. So as I understand it, one of the things that Trump is interested in with things like tariffs and others is, how do I eventually make income tax equal zero as a way of doing, UBI or some other mechanism, and make the technology, the robots and such, be the entire economy, right?
Yeah, but you see, here's the rub, because these timelines don't overlap. And that's the challenge, and that comes back to the question of.
So actually,
I think so.
We're going to see in 2026, either 2026, 2027, either the AI data center build stuff is increasing the economy as well as AI productivity, or it's not, because we have a projection from Lutnick and from Besant that we're going to get to 6% GDP growth in the United States, right? That is based on AI data center investment and AI data center productivity, right? So the traditional AI doesn't do it. We're at 2% GDP growth.
Yes,
right?
Exactly.
And right now we're at 4%. So people think, oh, either 4%, a bubble, this or that, blah, blah, blah. if we go up and things start ratcheting up to 6% sustainable 2026, 2027. And that's from like the $1.5 trillion investment from tariffs, from purchases, and from these AI data center builds. The AI data center build is like half of it, right? So that goes to, if space AI data center construction and build is the only way to sustain it, right? Then that would be like $2 trillion. It'd be like 10 times the level that we're doing now, right?
Mhm.
So instead of just a 2% GDP growth just from the build, just from building it, then you could be looking at 10% GDP growth, whatever. So then you're
Okay.
saying, who's going to stop it? It's like, I'm going to go from 10% GDP growth to 2%.
Yeah, but I'll tell you what the problem is, and that's going to be the point where money needs to keep flowing back to people, because that's going to take away white collar jobs as well as blue collar jobs, because by then you'll have the deployment of AI agents, not only for intelligent work but also for labor, in the form of humanoid bots, right? And then you'll have to talk about something like UBI, universal basic income, or some
Right.
tax break in a combination with a UBI, because it just boils
Well,
down to management of society, and that plays into politics. And therefore,
right.
my question about 2028 and the continuing of an enabling political environment, how do you build that?
If I can sort of add to that, I think that rather than looking at it in that way, I'd look at it as like I think it was Alex Wiesner Gross was pointing out a couple of things. One, he asserts that the singularity is like going into a black hole, and that it's flat while you're going through it. And that all of the changes that those of us that spend our time looking at are focused on, right? But the point that he'd made was that apparently we're looking at an annual reduction in the cost of intelligence, i.e. everyone on the planet has access to smarter, 40x every year, and accelerating according to Kurzweil's law.
Correct. But I also think it's an assumption to think that that this very point you're making, that the access to a much more effective intelligence, personalized intelligence, is going to result in individual productivity boost.
No, it results first in corporate boosts,
Right.
and then it
But
becomes
corporate boost
embodied.
equals job losses as well. Because
Understandable, right? But there's two things to note. The first is that it's inevitable that the humans are going to get disrupted, both in physical and cognitive labor. But the second is that in terms of governments and nation states trying to, one, rely on the inherent bureaucracy of flawed human systems and corruption and yada, 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 and two, to fool all of the people all of the time, when there is in fact some sort of access on a ubiquitous basis, so that people can throw things into Grok or whatever. Look at this from a societal basis, that you now have tools where thinking people can say, oh, is this right, wrong, or do my research. This is something that's never really existed in all of human experience, and be able to get an answer that you could reasonably trust.
Yeah, I'm a skeptic.
So a quick point about the skepticism.
Yeah.
So
well, it's preferable to human answers, is my point. Right?
So
every day it's more preferable.
So just 6% GDP growth, right? Which we're already talking about, right? And it's based on the spending that we're talking about here, and then having that pay off, right? That level of 6% for the next 3 years, right? The difference between that path of 6% in 2026, 6% in 2027, 6% in 2028, and then accelerating beyond that, because I'm saying we're going to go to 10 times more construction, right? Is 20% over a 4-year presidential term.
Right.
I'm either having a economy that's $30 trillion, or I'm having an economy that's $36 trillion. And what does that mean? That means that my deficit went down by $1 trillion a year. Right? Because now it's flowing back in. And then if this gets bigger, 8%, 10% GDP growth, that means over a 4-year time frame, right? Versus the differential of staying at 2%. right? I've gone to China late 1980, 1990 levels of growth at 10%, right?
Right.
I'm doubling my economy every 6-7 years, right?
Yes.
So that kind of like abundance
That's
craziness.
that's all rights law stuff. I mean, if you
Yeah.
basically suggest that Tesla, I've said this to many people, Elon said this to Trump. Okay, first caveat. Hey, Tesla's going to 10x over the next 4 years. We're going to build robots and all this other cool stuff. And you then say, can Trump Teslafy America? Automated production, AI, all of that. If he can, and he does it for Tesla shareholders over the course of the next few years, will America have 10x GDP like Tesla has 10x market cap as a way of doing this is how we get AI on board. Thoughts?
So yeah, so that'll take, 10, 20 years, probably 20 years after that to achieve that kind of goal. But then you're looking at an economy that's $300 trillion, $500 trillion per year, just in the United States, and then you do that for the rest of the world, and that is the abundance. And people say, well, that's impossible. You look at the Industrial Revolution over 60
Or
years.
you just say, what does Elon mean when he says that robots are the infinite money glitch?
Yes.
Right.
And
right.
that money means nothing.
That
if we
is a
go back
statement that
20
scares
years.
the bejesus out of me, because that has a great amount of social and labor implications, and I don't think American society
Well,
is ready for that.
Right, but it also is the destructive creation from capitalism to abundance. How do
Yeah,
you
but
get?
it's easier to do that in China than in America. Let's be real about this.
No,
So
it's just as easy in both cases. It's a question of willingness to, it, go beyond people's personal linear thinking and go, this is the time. It is
Yeah, and
driven because
democracy
of the
isn't the system
singularity.
for that.
Correct. So that means that the leaders in the world are going to do what they've always done, which is stick handle the populace in their relative jurisdictions and see if they can manage to retain power as long as possible while all the ships go down. Right? And, when you look at this maybe happening in 26, 27, mass layoffs, I mean,
Yeah, I know. It's like,
I've spoken with many politicians and they look at me like, you mean my reelection is going to be dependent on the fact that half of my
exactly.
right? And it's
Exactly.
like
Because
they go blank.
I fear that, I mean, look, all of this is wonderful, but there are assumptions here that all creatures, great and small, all things bright and beautiful, and all humans are equal, all intellects are equal, all societies are equal. There are a
That's
lot
the
of
problem with the left
there are
or
a lot
the woke messaging, right?
exactly, and
Yeah.
so I put this to you, that there are very real world issues in society, in American politics, that could just unravel all of this very quickly.
So as I'm saying that just 6% GDP growth, we can probably balance the budget in like 6 years, right? And if you can balance the budget, you would say, I'm not going to balance the budget. I'm going to still spend another trillion or 2 trillion per year for handouts, and then that safety net becomes stronger, right?
And
In terms of
do you know where that number comes from, Brian? Just to sorry for interrupting.
Yeah.
Is whatever you pick that rate. Joe Backley talked about this as well, and that there are cases where you've gotten 10% or more in U.S. growth. This is rights law expressing itself, and the shift to what you build and the learning rate. So if we discussed before, PV cells at 20%, batteries at 18%, there is an underlying potential to improve the economy, the ability to produce things in a manufacturing sense, by 18 to 20% a year, if in those technologies. And that will come out for everyone. So that's another thing to really point out, is that these are key technologies, and they already have very high learning rates, which means we get very rapid doubling and return on our investment.
All right, we'll have to leave it at that for today. Thank you so much, Brian and Chris. It's been a pleasure, and I hope to see you again soon.